Welcome to Texas State University's Organic Chemistry 2342, Organic Chemistry 2. We're going to continue on with Chapter 12, Part 1, Alcohols and Carbonyl Compounds. So let's first talk about the carbonyl group. The carbonyl group is a class of groups containing a carbon-oxygen double bond, and it can be used in a variety of different functional groups. For example, we can have an aldehyde if we have it bonded to a single carbon and a hydrogen, a ketone if it's bonded to two carbons, a carboxylic acid if it's bonded to a carbon and an OH. We then have carboxylic acid derivatives of an ester, which is bonding it to another alkyl group. And then we have amides, and then we also have acid halides. That's where this R group, the X group here can be fluorine, chlorine, bromine, or iodine. Most commonly, though, it is the chlorine. One of the functions about the carbonyl compounds is that it is a sp2 hybridized carbon and therefore has a double bond to the oxygen with the p orbitals. This gives it a 120-degree trigonal planar structure and approximately 120 degrees between all three substituents here. The other thing it has is a resonance structure that allows it to have a partially negative charge on the oxygen and a partially positive charge on the carbon. If you look at it in its two most extreme states, we have a no charge state here, and then a fully charged state here, where the oxygen is taking on the full negative charge and the carbon has a full positive charge. Which that would lead us to our hybrid resonance structure right here, where we have a partially positive carbon and a partially negative oxygen. We're going to use that polarized bond between the carbon and the oxygen to allow us to do additional chemistry on it. Okay, so one of the things it can do is if you have your carbonyl compound, remembering that this is your partially positive side, it will react with nucleophiles to create a new sigma bond. Remember, nucleophiles are those with a lone pair or a negative charge. That will come in here and create a new sigma bond, giving us our new functional group. An R group here and an R group here. Okay, so those R groups can, of course, be hydrogen or other things. When we do this, this is an addition reaction, converting it from an sp2 hybridized carbon to an sp3 hybridized carbon. The other opportunity we have with it is the availability of doing an oxidation and reduction reaction. For example, we can start with an sp3 hybridized carbon, and as long as there are hydrogens available to us to take off that carbon, we can oxidize that material to give us our carbonyl compound, where two of the hydrogens have been removed from our system. Or we can take that carbonyl compound and actually go in the opposite direction and do a reduction reaction on that system. And in this case, we're going from a primary alcohol to an aldehyde, okay? Now let's review redox reactions or oxidation reduction reactions. In our inorganic oxidation reduction reactions, we typically think about the loss or gain of electrons. For example, oxidation is always the loss of electrons from a metal center, and reduction is always the gain of electrons from a metal center. However, we have slightly different rules in organic chemistry. In organic chemistry, we use it where the increase in the number of bonds to nitrogen, oxygen, or a halogen is oxidation, or a decrease in the number of bonds to hydrogen is oxygen. That means the reduction would be the opposite of that. An increasing number of bonds to hydrogen is a reduction, or a decreasing number of bonds to nitrogen, oxygen, or halogen. Okay, so for example, if we start with a organic molecule here, just a general organic molecule with 3 hydrogens at the end of our chain here, we can oxidize this down to our first oxidized state, which is removing one of those hydrogens and increasing our bonding to oxygen by 1 and giving us our primary alcohol. We could also then reduce this down and get it back from that primary alcohol down to that alkane. We can also go and increase our oxidation again by removing another one of our hydrogens and in doing so, we would create another bond to oxygen. In this case, we're going to generate a carbonyl compound. We're still going to have that hydrogen on there and that R group on there. But again, we can go from this aldehyde functionality back to that primary alcohol in a reduction step. And we can even oxidize this even further by oxidizing off our last hydrogen to generate our carboxylic acid in this case, right here. But we can also reduce that carboxylic acid first down to the aldehyde, then the alcohol, and then all the way down to the alkane. So this is the process of organic redox or reduction oxidation processes that we're going to learn about in this chapter. Okay, so the first thing we need to think about is what is the oxidation state on each individual carbon in a system? And so we assign a system to that by taking a +1 oxidation state for each bond of an atom of a more electronegative atom, meaning nitrogen, oxygen, sulfur, or any halogen, okay? Now, we'll take and assign a -1 unit to each atom that is less electronegative than carbon, typically hydrogen, but that does include lithium and magnesium. Now, carbon-carbon bonds don't count toward the oxidation state, so we leave that at 0. So if we were to draw our ethanol compound right here and start looking at the oxidation state for carbon number 1 and carbon number 2, in carbon number 1, we have to remember that we have 2 hydrogens here and 3 hydrogens on our terminal carbon here. So for our carbon 1, we're going to get a +1 for being bonded to the oxygen. So, and then we'll get a -1 for each of the hydrogens, giving us a net oxidation state of -1 for carbon number 1. So let's look at carbon number 2. We have a carbon-carbon bond, and that, of course, is 0 units. So all we have to do is do a -1 for each of the 3 hydrogens. Therefore, carbon 2 has an oxidation state of -3. Okay. The lowest oxidation state possible is in methane, where we have 4 hydrogens bonded to it, and that would be an oxidation state of -4. Okay, let's do the same thing for our formic acid, making sure we take into account each bond to an atom. So we have on here our hydrogen, which is our -1 for our hydrogen. We have 2 bonds to oxygen in our carbonyl. So that's +2 for each of those, +1 for each of those bonds, giving us a +2 for the carbonyl. And then we have another bond to oxygen for another +1, giving us a net of +2 as our oxidation state for our carbon in formic acid. Okay, it's very important to be able to calculate the oxidation state of these systems. Now, the highest oxidation state possible would be something like a carbonic acid, where we have 2 different hydroxides bonded to, and the carbonyl, giving us an oxidation state of +4. So carbonic acid would be our highest oxidation state possible, and methane is our lowest oxidation state possible. Okay, so let's talk about that in a little more detail. So when we're thinking about synthesizing alcohols via these reductions of carbonyl compounds, we can take any carbonyl derivative right here that has just 1 carbon bonded to it and any other electronegative atom. For example, the carboxylic acid, the carboxylic ester, the aldehyde, or an acid halide here. And that will convert them down to primary alcohols, because it's going to reduce the carbonyl down to the OH and reduce off the other electronegative groups. So these will all give us primary alcohols. Okay. However, if we have ketones right here, we have 2 R groups already bonded to the system. The reducing agents do not reduce off that carbon-carbon bond and only reduce the oxygen-carbon bonds, and therefore we'll get secondary alcohols where we have R, R, O, H, H. So When we're thinking about these groups, anything with more than the carbonyl is going to be reduced down to the primary alcohols. Anything with two R groups can only be reduced down to a secondary alcohol. Okay, now that we're looking at reducing these carbonyl compounds, let's talk about the different reagents we can use for this. The first reagent we're going to talk about is lithium aluminum hydride. Okay, this is a very strong reducing agent, and the active species is the hydride, which is a hydrogen with a -1 charge. Okay, so it has both electrons in that s orbital, and therefore it is a very strong reducing agent in the system. This was so strong that it'll reduce down carboxylic acids and esters all the way down to alcohols. It will also reduce down ketones, aldehydes, and and acid chlorides. However, you typically don't use on this because we have another reagent we use for those groups. The other thing we have to realize is that this lithium aluminum hydride is very reactive. It reacts very violently with water, even water, alcohols, and all acids. So we typically run this in diethyl ether. So you'll typically see lithium aluminum hydride in ether as our material. And then a second step would be to add water to decompose the material. So what that would look like is we would have our carboxylic acid right here, and then we'd say 1 lithium aluminum hydride, 2 is water or acid. And that'll reduce it down to a primary alcohol. The carbonyl carbon now has 2 hydrogens on it, and we still have an OH on there. So this is a very typical reaction, and it also, again, works with esters. Okay, so let's say we wanted to do a reduction on an aldehyde, ketone, or acid chloride. Okay, we would use a different reagent with this. We would use a reagent called sodium borohydride. And so sodium borohydride will take any aldehyde or ketone and reduce it down to either a primary or secondary alcohol. And that would look like sodium borohydride. Plus, we would also quench with water or some kind of acid at the end to give us back our primary alcohol. We would end up with 2 hydrogens on the carbonyl carbon and an OH. Okay, so this works with aldehydes, ketones, and acid chlorides. It takes them all the way down to primary or secondary alcohols in the case of ketones. It is not strong enough to reduce down the carboxylic acids or esters, and therefore it is safe to use in water and alcohol. So you can quench the reaction, you can even run the reaction in water and alcohols to generate your primary alcohol, as long as you add a little acid at the end to decompose the boron complex. Now, the way this works is we have our boron species at the center, and it's bonded to 4 hydrogens here. Now, boron typically wants to have 3 bonds, so that's going to give us a negative charge on this boron here, which means the hydrogen is going to act as the nucleophile and attack the carbonyl hydrogen. And in this case, I'll use a ketone. It's going to attack that carbonyl carbon and generate our new sp3 hybridized bond plus a negative charge on our oxygen here, which then will be decomposed with the presence of any proton available to it, such as that with water or another alcohol, to generate our new primary or secondary alcohol. Okay, so again, if it's a ketone, you end up with a secondary alcohol. If it's an aldehyde or acid chloride, you end up with a primary alcohol. Okay, so in summary, we have 2 different reagents that will reduce down these carbonyl compounds. And so we have selectivity in our reduction because one of them is very strong and will reduce down carboxylic acids, carboxylic acid salts, and it'll also reduce down esters. And that reagent we have, of course, is the lithium aluminum hydride. Will reduce down those 2 groups. But Sodium borohydride is not strong enough to reduce these down, so we can use sodium borohydride to reduce down things that are less oxidized and acid chlorides as well. Oops, ran out of room. Okay, so we can use sodium borohydride to do these, but we can use lithium aluminum hydride to do all of the above right here. Okay, so what this gives us is it gives us an opportunity to be very selective about which groups we reduce down. So for example, if we had a compound that looked like this, and we used sodium borohydride on the system, it would only reduce down our ketone at the end and give us our carboxylic acid, and then our ketone here would be reduced down to our primary alcohol selectivity in the presence of that carboxylic acid. What's also important to note here is that that aldehydes will reduce faster than ketones. So in the case of this reaction, if we were to have, instead of that carboxylic acid, we had an aldehyde here, the aldehyde would reduce first, giving us our primary alcohol and our ketone still intact. Okay, so now we have selectivity in our reduction. We can reduce down just the ketone in the presence of a carboxylic acid or an ester. We can reduce down just the aldehyde in the presence of a ketone as carboxylic acid or ester. Or we can use a very strong reducing agent and reduce down our carboxylic acids and our esters using lithium aluminum hydride. And that concludes section 12.2.